All right, let's just jump right in. We're going to be talking about a theory today that is, well, it's pretty wild. It doesn't just tinker with our picture of the universe, it basically throws the whole thing out and starts over. So what if I told you that space-time, gravity, even matter, none of it is fundamental? What if it all emerges from something much, much deeper, just pure quantum information?
So here's how we're going to break this down. First, we'll look at the big problems in physics that have everyone stumped. Then we'll dive into this new idea, this quantum source code for gravity. We'll explore how it suggests space-time is actually built from entanglement. After that, we'll see how it's actually being put to the test. And finally, we'll ask the big question, could this be a path to a truly unified reality?
All right, first up, the cracks in our cosmos. You see, for the better part of a century, we've had this incredible model called lambda-CDM. It's been the king of cosmology, but it's starting to show some pretty serious cracks.
Now, this model, lambda-CDM, has been the bedrock for decades. I mean, it's been stunningly accurate. It's basically general relativity plus two, let's be honest, pretty mysterious ingredients. You've got lambda, which is our stand-in for dark energy, and then cold dark matter, or CDM, which is the invisible glue holding galaxies together. It's the best picture we've ever had of the universe, mostly.
And this right here is probably the biggest crack of all. It's called the Hubble tension. It's like this. When we look at the universe nearby, using things like supernova, we measure how fast it's expanding, and we get a certain number. But then, when we look all the way back to the early universe, at the light from the Big Bang itself, and use our theories to calculate how fast the universe should be expanding today, we get a completely different number. And the thing is, these two numbers, they just don't agree, not even close.
And look, this isn't some small measurement error we're talking about. The disagreement is huge. With some data, it hits 5.4 sigma. Now, to put that in perspective for you, in particle physics, 5 sigma is the gold standard. It's the level of certainty you need to announce you've discovered a new particle, like the Higgs boson. So this isn't just a little puzzle. It's a gaping hole in our understanding. It's screaming that we're missing something really, really fundamental.
So what gives? How do you fix a problem this big? Well, what if the issue isn't some new particle we haven't found yet? What if the problem is gravity itself? What if our whole theory of gravity is incomplete? And that brings us to this new idea, Qμ-Modified Gravity.
Okay, so what is this Qμ-Modified Gravity, or Qμ-VMG? Well, it's a direct modification to Einstein's famous equations. You know, the ones that say mass and energy tell space-time how to curve. This theory says, hold on, there's another piece to the puzzle. It adds this new term, Qμ, which basically says that gravity doesn't just come from stuff, from mass and energy. It also comes from the quantum information that's packed into the vacuum of space itself.
So, naturally, the big question is, what exactly is this Qμ term? I mean, where does it even come from? If there's a whole new source for gravity, what is it? And to answer that, we have to go from the scale of the entire cosmos all the way down into the weird, wonderful world of the quantum.
And this is where the theory gets truly mind-bending. It suggests that space-time itself, the very fabric of reality, isn't fundamental. It's not the base layer. Instead, it's an emergent property. Think about it like the wetness of water. A single H2O molecule isn't wet, but a whole bunch of them together are. Space-time, this theory says, is like that. It emerges from a deeper layer of quantum entanglement.
So how does this work? Well, it's this really elegant feedback loop. Check this out. It starts with curved space-time. Because of a weird quantum rule called the Unruh effect, that curvature actually generates a tiny bit of heat, a temperature. Now that temperature changes the quantum entanglement between little bits of information in the vacuum. And here is the craziest part. The pattern of that entanglement is what creates the geometry of spacetime to begin with. It's a loop where spacetime geometry creates entanglement patterns that create spacetime geometry.
So the main idea here is that spacetime isn't some pre-existing stage that physics happens on. It's actually part of the show. It's an emergent property. The best analogy is your computer screen. You see a smooth picture, right? But you know that if you zoom way in, it's all just individual pixels. This theory is saying our smooth continuous universe is just like that screen. It's an illusion that emerges from a massive network of quantum pixels.
And this idea isn't totally out of left field. It actually gets some support from a branch of physics called causal set theory. The thinking there is super elegant. It basically says geometry is just two things. Order, which is how things are connected, what causes what, and number, which is just how many things there are. You put those two together, order plus number, and poof, you get geometry.
Okay, I know this sounds like some pretty wild philosophical stuff, but here's the most important part.
This isn't just a cool idea. Qμ-Modified Gravity makes very specific, testable predictions. This is real science. You can actually go out and look for evidence, and if it's not there, the theory is wrong.
So how are scientists putting it to the test? Well, they're attacking it from a few different angles. First, they're looking at the cosmic microwave background, that baby picture of the universe. The theory predicts a specific kind of gravitational lensing, and what's wild is that the Planck satellite data already shows a little hint of it. Second, they're looking at how galaxies are clustered together. And third, they think they can actually build experiments in a lab to detect the Unruh effect directly.
But one of the biggest tests, a real high-priority one, has to do with how galaxies are spread out across the universe. And this is what's so powerful about the theory. It doesn't just say things should look different. No, it makes an incredibly precise prediction. It says there must be a specific logarithmic relationship between space-time curvature and this quantum entanglement. And it gets even better. It predicts the slope of the graph for that relationship has to be 1, give or take a tiny little bit. It's incredibly specific.
And get this, early analysis from a huge galaxy survey, the Sloan Digital Sky Survey, actually shows a correlation that fits that exact logarithmic shape. The stats are pretty good too, less than a 1% chance that it's just a random coincidence. Now, we have to be careful. This isn't proof, not yet, but it is one heck of a compelling hint that they might really be onto something here.
Okay, so let's zoom out. What's the big takeaway here? If this theory pans out, it's not just about fixing a few cracks in cosmology. We're talking about a fundamental shift in how we see reality itself.
The grand vision here is, well, it's huge. The hope is that this could solve those big cosmological problems, like the Hubble tension. It could finally unite general relativity and quantum mechanics, the two great theories of the 20th century that have never played nice together. The real goal isn't to make things more complicated, it's actually to make them simpler, to show that everything we see, all of it, gravity, space-time, matter, it all emerges from one underlying reality built from quantum information.
So I'll just leave you with this final thought. We always think of space-time as the stage, right? The fixed, unchanging background where all the action of the universe happens. But what if that's totally wrong? What if space-time isn't the stage at all, but one of the main actors, constantly being shaped and rewritten by the quantum information playing out within it?